State the connection between derivatives and continuity. So first off, we're going to talk about the relationship between continuity and derivatives. But before we can do that, we got to go over some basic terminology that has to do with derivatives, because now that we're using derivatives, we need to know what the instructions are describing or what we're being asked to do. So we know that the derivative is the slope of the tangent line. So finding the derivative will allow us to know what the slope of the tangent line is at a specific point on a curve. Then, to differentiate, this is the action of actually taking the derivative. So to find the derivative of a function, I'm going to want to differentiate. Then, we say a function is differentiable if the derivative can be taken. So basically, if we can take the derivative, then that particular function is differentiable. And then finally, the huge umbrella term is differentiation. And differentiation is the algebraic method to finding the derivative. And again, all of these terms are important for when you're reading directions and trying to figure out what to do for each problem. So now we can talk about the relationship between continuity and derivatives. And here we have a theorem. It is loosely called differentiability implies continuity. And the name of the theorem kind of gives it away, as you can see. It states that if f is differentiable at a point A, then f is also continuous at a point A. So let's break this down. So first off, let's talk about what it means for a function to be differentiable. Well, as we previously stated, a function is differentiable if we can actually take the derivative. And to take the derivative, we're going to need to use our limit definition of a derivative that states the limit as h approaches 0 of f of a plus h minus f of a all over h equals some number. And if we are able to actually evaluate the limit, and the limit does equal a number, that means that the derivative at x equals a exists. So again, if these statements are true, then we know f is continuous. So what do we know, or what does it mean for a function to be continuous? We've fortunately already covered this. We know that there are three conditions for a function to be continuous at a specific point. We know that f of a has to be defined. We know the limit from the left and the limit from the right must equal the same number, telling us that the limit exists. And then finally, the limit has to equal the function, i.e. the intended height has to equal the actual height. So now, what does this mean in terms of our theorem? Well, quickly, let's just go back and let's take a look at what our theorem says. It says that if f is differentiable at a, well, we now know what that means. If f is differentiable at a, that means f prime of a is going to equal the limit as h approaches 0 of f of a plus h minus f of a all over h equals some number. Then f of x is continuous at a. Well, we know that if f is continuous, that means that f of a is defined, the limit exists, and the limit equals f of a. So again, breaking down this theorem, it says if f prime of a equals the limit, and that equals a number, then the three conditions of continuity are true. Alright, then we have another theorem that tells us that if a function is not continuous at a, then it is not possible to find a derivative at a. So not continuous implies not differentiable. So in order for us to take the derivative, the function has to be continuous. Now this next one is a trap function because a lot of folks like to think that this is true. But it's not true, which is why I titled this Not a Theorem. Because this is a false statement, but something that a lot of students get kind of tricked into thinking, and we're going to do our best to avoid that here. And this not a theorem, or a fake theorem, claims that if f is continuous at a, then f is differentiable at a. And this is 100% absolutely false. And we already have an example that we've looked at that proves to us this is wrong, and that is the absolute value function. because as we can see here and as we previously talked about, this function is continuous. However, at the vertex of the absolute value function, we can see that we have a corner, or we have an immediate change in direction, a sharp change. And we know that whenever we have a corner or a sharp change, we know that we don't have a derivative. So here is a counterexample to this fake theorem. So therefore, just because something's continuous doesn't mean we can differentiate it. So that's all of our theorems, 2 real ones and 1 fake one. So let's start looking at some examples. So this example says, given the following limit, the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h equals 8. Which of the following must be true? Well, to solve this problem, we're going to ignore those choices for now, and we're just going to write down everything that we know is true based on our differentiability implies continuity theorem. So let's see. Well, this particular expression looks oddly like the limit as x approaches 0 of f of a plus h minus f of a all over h equals f prime of a. So from this limit, we can tell that a is going to be 3, and then therefore f prime of a is going to be 8. So again, we can just write down what we know. So we know that a is going to be 3. We know that f prime of 3 is going to be 8, since a is equal to 3. And this shows us that the function is differentiable at 3, because we can find a derivative. And since a function is differentiable, that means it's also continuous. So we also know that f of 3 is defined. We don't know what that is based on the information we're given, but because it's continuous, we know that has to be true. We know the limit as x approaches our a value, which is 3, of f of x exists. Again, we know nothing about where it exists, but because it's continuous, we know it does. And then finally, we know that the limit of f of x as x approaches 3 has to equal the actual height f of 3. So that is everything we know. So now let's come and check off which of the following statements are true. Well, let's see, the first statement is f of x is continuous at x equals 7. Well, according to our analysis here, since it is differentiable, we know that it is differentiable at x equals 3, not x equals 7. So that first choice is out of here. All right, next up, we have the limit as x approaches 8 of f of x equals 3. And this one is also wrong. And this one's a trap because the 3 is really our a value, and the 8 is really the derivative. So they just use numbers that are in the problem to try to trick you. And as we can see, this is all wrong. So it's All right, the next limit is the limit as x approaches 11 of f of x exists. Well, we know the limit exists, but it's the limit as x approaches 3. So that is also out of here. Next up, we have the limit as x approaches 3 of f of x equals f of 3, and that is our third condition of continuity, so that is a correct answer. Ding, 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 ding. And lastly, we have the limit as x approaches 3 of f of x equals 8. This is another trap answer because we do have a limit that does equal 8, but that's the definition of the derivative, not the limit of our function. So again, wrong. Meaning that in this particular answer, the only answer choice that is correct is this fourth one. So again, be careful. These questions are going to try to trick you by using numbers or situations that look similar or that are pulled from the problem, but are just used in the incorrect way. All right, next example. Suppose f of x is continuous at x equals 4, and that f of 4 equals negative 3. Which of the following must be true? Well, if f of x is continuous at 4, we know that a is going to be 4. So therefore, f of a is defined. And we know that f of 4 is going to be negative 3. So we know that piece of information too. Since this function is continuous, we also know the limit as x approaches our a value, which is 4, of our function f of x exists. And we know the third condition, the limit as x approaches 4 of f of x, has to equal f of 4. And well, we already know that f of 4 is equal to negative 3, so we can substitute that in and find out that the limit as x approaches 4 of f of x also equals negative 3. Alright, so now it's time to get to work. Which of these following statements must be true? Now the first statement says f of x is differentiable at x equals 4. Well, this is where that fake theorem comes into play, because that fake theorem tried to tell us that if something's continuous, then it's differentiable, which it's not. That's the opposite. So don't fall into that trap answer, because that is wrong. All right, next up we have the limit as x approaches negative 3 exists. Again, we do have a limit that exists, but it's based around our a value 4, not negative 3. Trap answer. Done. Let's see, the limit as x approaches 4 of f of x equals 2. Well, we've already figured out the limit as x approaches 4 of f of x equals negative 3, so that one's gone. Let's see, next up, the limit as x approaches 4 of f of x exists. Ding, 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 ding. We've already proved that one, so that is a answer choice. The limit as x approaches 4 of f of x equals negative 3, again, we've also done that one, so ding, 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 ding. And then finally, the limit as x approaches negative 3 of f of x equals 4. That is a trap answer, because again, it's using numbers that are in the problem. It's just using them in incorrect ways. So we can throw that answer out of here. So in this particular case, answer choice 4 and answer choice 5 are the two correct ones. All right, so for our last example, we can see that given that the function g of x is differentiable at x equals negative 2, and that g of negative 2 equals 7 and g prime of negative 2 equals negative 5, which of the following must be true? All right, so let's go ahead and write down everything we know. So first off, we can see that our a value is going to be negative 2. We are told that the function is differentiable. So therefore, a prime of negative 2 exists. And we can see in the problem that g prime of negative 2 is going to be negative 5. And we also know that the limit as h approaches 0 of g of negative 2 plus h minus g of negative 2 all over h is going to be negative 5 as well, because those are both g prime of negative 2. Now, since we know that g is differentiable, based on our theorem, we know that g is also continuous. So we know that g of negative 2 is defined. And from our problem, we know that g of negative 2 is going to be 7. We also know that the limit as x approaches negative 2 of f of x will exist. And then we know the third condition, the limit as x approaches negative 2 of f of x has to equal, and I've just realized I'm using the wrong function here, so let me just go back and fix that, because it's not f, it's g. Sorry about that. And so then we have the limit as x approaches negative 2 of gx exists, and the limit as x approaches negative 2 of g of x is going to equal g of negative 2, and the problem tells us that g of negative 2 is going to be 7. All right, so now we can look at our answer choices. The first answer choice is the limit as x approaches negative 2 of g of x exists, and we have that. Woo! So check, check. The limit as x approaches negative 2 of g of x equals negative 5. That is an They're trying to trick you with the negative 5 from the derivative, but that's not what the limit represents. Next up, the limit as x approaches 7, and right away there, 7 is what g equals. 7 is not our a value. We know our a value is negative 2. Next up, the limit as x approaches negative 2 of g of x equals 7, and we have that one, so that is an answer. And then the limit as x approaches 7, Again, 7 is not our A value, so that one is false. So answer choice 1 and answer choice 4 happen to be our statements that must be true given the information that we are given. All right, and I just wanted to quickly emphasize this, that differentiability implies continuity. That's the good theorem. Then the theorem that doesn't exist, the fake theorem, is continuity implies differentiation, so I changed it. So continuity does not imply differentiation. So please, 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 please keep these in mind, keep them straight, and learn them quickly. All right, folks, that is it. That is stating the connection between derivatives and continuity.